Sharon is a senior architect at Cadence and received his BA in computer science from Bar-Ilan University. Apologize if that's not pronounced correctly. He joined Veracity Design in 1996 and led the hardware test bench automation revolution as technical lead of the Cadence UVM team. Sharon co-authored the book, A Practical Guide to Adopting the Universal Verification Methodology, and is currently driving portable stimuli solution technology for SOC verification and represents Cadence in the Accelera Portable Stimulus Working Group. Thank you, Sharon. We appreciate it.
Thank you so much. Okay, hi everybody. Excellent presentation from both Adnan and Tom. So I think this will actually serve this presentation as well. And I'm going to talk about what are the guidelines. If I'm about to write PSS, what are the first things I need to know? How do I keep things modular and portable, etc. when building the PSS model? So we're going to build on top of some of the stuff that you've seen in the previous presentation. And the first question to be asked, let's see if I can move these, is let's talk about PSS and what we did for you with PSS. So if you guys have UVM background, right, we have UVM sequences. What do we need UVM sequences on top of PSS? Well, actually, we have action and activities. They have stronger solving capabilities with all this declarative style that Tom mentioned, and the inputs and outputs that are amassed, as Adnan said. There's partial specification. It's portable to all platforms. As was said here, the rules, the connectivity between subsystems is governed by constraints and dependencies rules. So we know by construction that the tests are going to be legal. You will have to do less debug if you use PSS versus UVM. Oh, that's so we do not need UVM sequences as in the methodology layer, right? It's native part of PSS. How about configuration of DUT and test bench? You know, we have UVM configuration mechanism in UVM. Well, we have memories, we have state variables that actually will help you find out and automatically find the right configuration for the right traffic. So this is a bidirectional relationship, right? I can put constraint on the traffic, constraint on the configuration. The tool can find the right mix, the right timing, etc. to enable that. Oh, that's quite an improvement. How about selfing's strategy? So we all know scoreboards and other reference models. These are still valuable. We're still going to use them, right? But the nice thing is that the PSS model itself could be the reference model. It actually could serve as a reference model. And if you're doing anything a little bit complex, like subsystem or SOC, writing those reference models could take a lot of time and a lot of maintenance. But you can actually use the tool to do self-checking for you. The PSS model with a PSS tool to do self-checking. That's an improvement right there. How about extensibility? That's the one that has a little bit of the blame or credit for the UVM factory. We added natively into PSS, aspect-oriented programming. And we have type override. So significant improvement in power, easier to use. Oh, we don't need that anymore as well. How about components for structure of the test bench? Well, like UVM components, well, we have native PSS components. They're part of the language now. No, we don't need those as well. Debug and visualization that Adnan mentioned, and I think Tom as well. Well, everybody can read activity diagrams. Everybody can read those charts. This is an excellent thing. And by the way, we chose activity of UML as both the terminology and the semantic of this new standard for a reason. It's easier to kind of describe what scenarios you want, but they also lend themselves very nicely into nice visualization, which one we're going to see in a minute. So great for us. And I would say that PSS, being part of a few standardization efforts, PSS has more native support for verification concept, whether it is resources in the declaration, state variables, all of these stuff are provided in PSS, native terms. By the way, we highly recommend to open the PSS LRM and read it. We made a big effort, now I'm talking on behalf of Accelerate right now, to just read the first section and, to see what it is about. I think that's going to be giving you a good sense of what we're shooting for and, why you should use that standard and not value tools providers like Mentor, like Breiter, and like us can provide for you if you use the standard input format in the designated way. So go ahead and read that. And the question that comes to mind is, well, we provided all that stuff. Do we need a methodology? And the answer is yes. The answer is yes, and let's try to answer that. So why do we need a PSS methodology? Or maybe there is a room for a generic library. So here is sort of a camera subsystem, and we're going to have a register file with registers that needs to be programmed. Now we're going to use a master, if it's a cordless environment, or a CPU to write to this camera. And the camera may read descriptors or will write traffic to some memory or a slave emulating that memory. It doesn't matter. So this is what you need to do. And I was said by the previous lecturers, and yeah, you need to create actions. PSS is about actions model. So you're going to create some kind of maybe capture actions, and it's going to have different styles of how do you do the capturing. And you're going to have an output, right? An output is a mask. So you're going to have an output that will write things to the memory, and you're going to consume the master or CPU core. You're going to lock it because it's, if it can do one thing at a time, there's no multi-threading, you're going to lock it. If it can do multiple things at a time, you can share it. It's all part of PSS. And so we're going to have a pool of these. And this requires a little bit of knowledge on how to do the modeling, how to model the pools and efforts. But it can be done. Now, if you look at it from the compute subsystem point of view, you may have CPUs that really call driver routines and activate things in C, or you will have masters that will call registered sequences, right? But they will do this essentially, if you take the level of abstraction up, they're doing read, write, copy to either registers or memory. These operations are joint, they are generic. They will be there in whatever environment, whatever implementation we have in there. They're definitely a candidate for a methodology or even a library. How about memories, right? We need to manage the memories, the data descriptors and the data itself. And as we put things in the memory, we don't want to override or have conflicts on memory. So that is yet another thing that needs to be done by a modeler as it creates a system for our camera IP, right? We need to do that. Let's move to a full system, but this is valid for subsystems as well. And here we have the multimedia or the graphic subsystem here, and they're going to create some kind of decode to display action, or maybe convert image action, or other activities that this IP can perform. And as you can see, it needs to read from memory and send to a channel with those PSS outputs that we've seen before. So here we are. We need to model these things, and we definitely want, and someone asked that question, well, we definitely want a scenario that will be a capture into the memory, read that in, and then decode that to the display, right? So this is what we want, and someone asked about it. I don't want to specify who's talking to who, right? I don't want to specify the path. I want everything that is possible out of the randomness to be created. Every legal programming to be created. I can choose that, right? But I don't want to go and specify, like Adnan mentioned, the million connectivities that could take place, right? So here it is. If these two things will write into a same type memory buffer, then they will work. And the DMA can read from that memory buffer. They can work automatically without us thinking about it. This is the declarative style, the open-ended approach that will find things we don't think of, like the delay that someone was asking about, right? So again, if I'm working on the decode to display, I need to write to memory and read from memory. I need to consume a master or a CPU core from a pool to do the programming. And this requires also some efforts, right? But unless there was some kind of upfront agreement between these two teams, they will not be able to talk to one another. Yes, you can create different kind of bridging, but why should you? Now, if you are created these standard actions here, then users can create other more abstracted actions. Like I want to create connectivity. I want all the processors to touch all the memories with all the boundaries. That could be out of the box. PSS allows you to create reuse and scenarios that topology independent that you would never able to create before. One processor writing to all the memories, to all the boundaries at the same time. How many processors? How many banks? You don't care. It's going to create it. So the fact that if you will have some activities, if you have some activities and actions that are part of a standard, then users, both vendors for commercial purposes or homegrown, will be able to create all these low power, performance, coherency, stress, connectivity scenarios that they will work on top of whatever model you have for the primitives, reads, and write. Okay? This is all reasons why it was very useful, both in terms of efforts of creating the PSS model, and in terms of know-how, I don't know how to create it, but also in terms of integration. It's a great framework for out-of-the-box integration between these models without any upfront planning. So this is why we need PSS methodology or a library, and it would be great to have guidelines and maybe codify best practices in a library. So, and that's what we're going to talk about today. How do you achieve that? I just want to say one thing. If you can read system Verilog and you can generate everything you want, then we made a mistake with PSS because I don't need a new language. But what we're doing is we added more semantic with the input and output, with the state variable, with configuration, that improve the solving for areas that UVM found hard to solve. That's what we're talking about. That's why you need the PSS methodology and library. And we're going to talk about how to, you need the PSS language. And we're going to talk about how to make it easier to define it and how to instruct a newbie on how to do it. Before we start, I didn't create my own, agenda of starting in 1955, etc. These are all users of the same guidelines and technology. We have hundreds of users starting from 2011, and they introduced terms that are uniquely defined in Perspec. This is the Cadence PSS tool, which were adopted. So terms like actions, input and output, components, resources, pools, and resource planes. All these were uniquely introduced by Cadence. That was in 2011, and you can see that some of the users have used graph technologies before and moved to what is now PSS. I'm not going to talk a lot about technology here, but this is something that is used by many users, and they following these guidelines. And if they don't need to learn what actions, input and output, and how to create activities and how these are solved together. They could teach all of us how to do it, and same all of us as vendors as well. We're already at that level that users are actually providing interesting things we didn't think of with those standards PSS concepts. So this is proven, and this is the library itself. We call it SML, System Methodology Library. It's in PSS. It includes both library and guidelines, proven over time, both commercial and homegrown, and of course, the ability to integrate homegrown and commercial action libraries. Apply for software-driven and pre-silicon, post-silicon, and of course, shifting across. We do provide an open source for the key base classes. You can try it with whatever PSS tool you want. We do add more automation that we gathered throughout the years on top of that library, and I'll give you a demo of some of that. As I said here, we're using DVT link tool to ensure that PSS, it's actually PSS compliant code. So we highly recommend doing that as well. So I'm not going to show you slides. I'm actually going to show you demo. So let's move to that demo real quick. So here's our here's a Perspec Composer tool, and as we said, Accelera selected activities and with UML terms and notions, and this is what this tool does. What you see in here is everything that was being modeled, right? So I can, let's look at the camera, and if you remember from Adnan short lesson, the camera that is doing capture is outputting a memory buffer, and I can put constraint that it's an image or video, or I can put constraint on the resolution, low to medium. And by the way, I'm locking the camera saying, oh, camera can only do one thing at a time. Okay, that is the definition of the camera, and start getting used to it. It's not a lot of code, right? Because of that level of abstraction, the code is short. We have an output, we have constraint on the output. And we're locking resources, in this case, just locking the camera itself, saying, oh, only one capture can happen at a certain point in time. Let's look at the modem, and you'll see that over and over again. Here's our modem component, and we have an action receive and action transmit. This is what the modem does. It does an output with the receive because we're going to receive the information and put it in memory, and we have action transmit that will going to output the input from the memory and send. And notice that I'm full duplex, so we created two pools. So I can lock the receiving, I can lock the transmitting, but these two can work at the same time. Similarly, we'll have the DMA. In the DMA, we have, in this simplified example, only two channels. Okay, so only two channels, and we're locking one of the channel, and notice I'm deriving from a data mover. I don't even need to specify the input and the output. Look at the amount of code that we're talking about it, and I hope it made sense. Everything is action, inputs, and outputs, and let's create a scenario. What I can do, I can drag one of these, clean this area a little bit, so we'll have more working space. There we go. I can drag one of the action, as was said, and basically say, I want this to take place. It's a goals-based approach. I want this to take place. If you click the solve button, now I will get a solution that tells me the story. It's implementation independent. Tell me the story of the scenario that was randomized here. What I asked for is in green here, the code to display, and these were automatically created. They receive, they show, here's a memory buffer, right? The input and output. And here's another one with a video stream. Now, notice, we looked at these code. These code snippets were very short, but look at the amount of information that I have. I have memory management here with multiple nodes, with policies. How do you want to consume the memory? First fit, random, best fit, all of that stuff. You can talk to the boundaries. You can do memory allocation of specific banks, right? Where do you want it to be consumed for? I can select the processor type, but wait a minute. I didn't show you in the source code where all these things are being specified. Well, all these things are being specified right here in Excel. Everybody can read Excel. So this is the configuration mechanism of memory of processors. You can specify the masters that you have, and that's it. The topology is there. Everybody can read it. You don't need to read System Verilog. You don't need to read C. You can just read it like that, and it will automatically populate the test bench as desired. So let's create one more scenario with that. I'll create something a little bit more complicated. Let's say we want to stress the memory, and you know, in PSS we have this schedule and all of these things. So I'm going to do something like that. I'm going to initialize 3 memory buffers, copy them all over, and then do read check at the end. So here it is. And for those who know, PSS allows you to do schedule, and I can do 3 times repeat. Here they are. And look at what I'm opening, the SML software operators. All these write data, read data, copy data, they're pre-provided with implementation in a fine way for ANSI C code. It's easier to provide out-of-the-box implementation, while you can always connect to a VIP very easily with the exec body, a term that we also introduced. So here it is. I'm doing write data. Remember, this is 3 times. I'm going to do, let's make it more interesting. I'm going to do a selection between copy. So I'm dragging this inside. I don't know what's the implementation language that is going to run, or transfer, and I'm going to do read check at the end. I don't have time to explain to you how it works, but trust me, this is going to create a self-checking scenario. Let's change this to be something more interesting, and I'm just going to click the solve button. So here's our scenario that got created. A lot of things are happening here. I can look at the timing, but I can look at this. Here's our chain. Let me color it for you because, you know, by action type. Okay, here it is. Reinitialization, copy them all over, and you can see the nice mix of copy and transfer, and read self-checking at the end. Now, if I want to do, this will take a lot of time to create, right? With CPU cores, with fork and join, with virtual sequencers, because there's multiple cores involved here waiting for one another. There is management of the channels of the DMA. That's a lot of work to create, and we can click a button and create something else if we want to. Just want to show you one more thing. I can click these and basically open the coverage if I want to review the coverage. And let's open this and do coverage group analysis. And you can see exactly what we tried and what we haven't tried. With the directions, reads and write, with the instruction with, all of this is coming out of the box. It wasn't there, right? It's coming out of the box. Okay, so this is what I wanted to show you, a little bit about maximization. Notice that I didn't run anything and I can still get coverage. We have gen time coverage and we have runtime coverage. And the beauty is you can get coverage in gen time and basically design your regression suite, right? But more than that, I can actually tell which activity will take place and which activity will not take place out of the randomness. This is probably addressing a little bit the question that was asked, well, I don't want to specify everything. I want the randomness to work for me. This is what it is. The scenarios themselves, I can take which scenario will take place out of the randomness, not by specifying deterministically what's there. And of course, the tool can generate while the coverage is missing and don't run scenarios which do not contribute, right? So you can create this kind of amazing coverage maximization with this technology, right? Anyway, back to our slides, and to finish.
Hi, Sharon. Thank you for that demonstration. It was really very interesting. We do have to move on, I'm afraid. I was just wondering if there's a quick question in Bristol, and then we can do one quick question and then move on.
Hi. The question is, you mentioned the open source system methodology library. I wondered if you could provide a link.
Yes, we are, and I was about to come to it in here. If you guys are interested to get the code and try it with whatever tool, whatever PSS tool, we'll be happy to provide it. Here's an email. Please shoot an email, and we will be happy to assist you with that.
Thank you, Sharon. Appreciate that. The slides will be online after the event anyway, so they'll be able to look that up, so they can contact you there. Thank you so much for your time today, Sharon. Really appreciate it. Thank you very much.